So we just talked about next steps. I have a few slides from week 5, believe it or not. I think like 3 or 4 slides on dummy-coded regression that we're going to cover. And then we're going to talk about homework number 3. And then we're going to spend the rest of the day talking about how do we diagnose the regression analysis that we just ran. How do we know, how can we be confident in the results? And we do that through collinearity diagnostics. Outliers, and their residual outliers is what we're looking at. And then influential cases that have a disproportionate impact on the estimates, that is the B's, when compared to other cases. And then at the end of week 6 PDF, there are some additional multiple regression topics. One being hierarchical regression, not to be confused with hierarchical linear modeling, 2 different things, but we're going to talk about hierarchical regression. We're going to talk about letting the machine select your variables for you, and we call that stepwise regression. There's a number of other names for that. Does that sound like a good idea? Letting the machine select, and it's used less today in academics, used more in sort of exploratory data analysis, although you do see it from time to time as a part of academic research. But it makes me cringe to think that we're not letting what should drive the variable selection. Yeah, not the machine. And so it's. But we're going to talk a little bit about it because it is a topic that comes up from time to time. And then the final topic is nonlinear regression. And we're going to cover as many of these additional topics as we can get through. And we may not get through all 3 of them today, but if we only get through one of them, that's where we'll stop. And then next week we're going to start anew with exploratory factor analysis. Okay? Fair enough? So this should be about where we left off last week. What's that?
Is it recording?
It is recording. This is where we left off last week. And so I want to talk about dummy variables and multiple regression in 2 contexts. One, if you only have dummy-coded variables in your analysis, and this would be typical of what you do if you're analyzing experimental data. And then the other context will be if we have dummy-coded variables and other continuous predictor variables as part of our analysis. And week 1, we talked about dummy coding variables, and you had to do some dummy coding variables for the missing data analysis, so it should be something that is sort of familiar. But remember, when we dummy code variables, we dummy code up k minus 1 different variables, where k is the number of groups we have. So if we have 3 groups, we only need to dummy code up 2 variables to represent those 3 groups, right? The third variable would be redundant information. We already know the third group because, in all likelihood, they would be zeros on both of the dummy-coded variables. And so coding up a third variable would be redundant information. And it would lead to singularity, where there would be perfect correlation between the 2 variables and that were dummy-coded up and the third variable. And so SPSS, or any other software for that matter, would either just crash and give you an error message, or like SPSS does, it just excludes, it picks one of the variables for you and excludes it. So we have to make sure that we are only dummy coding k minus 1 groups, and we call that group that's excluded the reference group in this context. So the implied group, or the group that would be 0 on all of the other variables, would be the reference group. And in a regression context, you want to think about what should be, or how do you want to code your variables in such a way that the reference group is the meaningful comparison that you want to make. So, for example, if we have an experimental study where we have some group that gets some stimulus message, call it stimulus number 1. Some other group that gets some other stimulus message, call that stimulus number 2, and a control group. In all likelihood, your data in SPSS probably would just indicate 1, 2, and 3, 3 being for the control group. It might be something different, but it may not. But let's just say that it was 1, 2, and 3. And if we were to dummy code this, we only need 2 new variables, right? K minus 1. And in this case, for me anyway, it makes sense in this context to have the control condition be the reference group or the implied group. Because then we're going to compare stimulus 1 to the control and stimulus 2 to the control, right? And so just remember that the group that's implied, or the K minus 1 group, the group that's left out, or the reference group, is the group that you're going to be comparing to. And in most cases, there's a way to do it that makes the most sense, given your theory, given your context, given your study. So if this were our data, variable 1, or dummy-coded variable 1, is going to be everybody whose stimulus 1 is going to be equal to 1, and everybody else will be equal to 0, right? And the dummy-coded variable number 2, called stimulus number 2, or stimulus number 2 is going to, the variable called dummy-coded variable number 2, stimulus number 2 is going to be equal to 1, and everything else will be equal to 0. And so 0 on both stimulus 1 and stimulus 2 would imply the control condition, right? Make sense? And so here is some data from a study that uses dummy-coded, exactly the same situation that we just talked about. The data is not all that, or the data isn't new data, but the context is a presidential election, and the dependent variable is how close the respondents feel to George W. Bush on some set of policy issues. Higher numbers mean they feel closer to him on that set of issues. And you can see from the frequencies that we have, and I just sort of want to walk through this, and then we'll look at the regression output, and we can then square these statistics with the regression output so you can understand how this particular analysis works. So we have 66 people who were in stimulus 1 condition, and this condition is they viewed George W. Bush's website for some period of time. I don't remember the period of time, for 10 minutes or 5 minutes, whatever it was. The 62 people in the Gore condition, where stimulus 2, of course, viewed Al Gore's website, and the control condition viewed some control website, probably ESPN or something that was non-political, non-public affairs, news-orientated content. And we had 62 people in that group. And if we look at the statistics for the dependent variable, the mean is 4.79 for those in the Bush condition, meaning that was the strength of how much they were in agreement with George W. Bush on the issues. The Gore condition was 5.02, meaning still measuring Bush issues, but they viewed Al Gore's website. And then finally, this is the control condition, okay? And it was 5.72 is the mean for that condition. And then these are the 2 dummy-coded variables with 66 ones matching the 66 in the Bush condition and the 62 matching the 62. Make sense so far? Would be easy enough to do if you had this data, or a set of data similar to this, yes? And so now the thing that is pertinent here is how do we interpret the results? And this is, again, only, there's no other variables other than the experimental conditions as independent variables. Just those two independent variables. And we can see, well, maybe you can't see from here, but you can see from your handout that the R square is significant. The R square is rather small though, right? But it's still greater than we'd expect to get by chance. It's significantly greater than 0, right? And so given that significance level over there, which is some p less than 0.05, right? So it's p less than 0.05. Then we can go ahead and look at the coefficients. And we can see from the coefficients that our predicted y is going to be equal to 5.715 plus 0.079 times the Bush variable minus 0.692 times the Gore variable, right? And when Bush and Gore are equal to 0, what is the predicted y? 5.71. And when Bush and Gore are equal to 0, what condition is represented? The control condition. And if you look at, right, when both of those are equal to 0, that's the control condition. And this 5.715 should be the mean that we have here for the control condition, 5.72. Control mean is 5.72, which we round this and we get 5.72. Okay, right? Yeah.
So, what if you have more groups than 2? Because really the control group is not, like, because in my data I have 3 conditions and I don't have a control condition.
Yeah, and so if you're going to use regression to analyze that data, you have to decide which of those groups do you want to be the reference group. Which one do you want to make? I mean, if theory suggests you should make all possible comparisons, then you probably would be better off not using regression. ANOVA would probably just be, you could do it with regression, but it would be a few more steps than what you'd want to go through here. If theory suggests you should do group 1 with group 2, group 1 with group 3, and group 2 with group 3, if that's what theory suggests, then probably ANOVA would be a better way to go. But if theory says maybe it's 1 with 2 and 1 with 3, then you can dummy code up the data in such a way that you have the correct reference group. Good question. Does that make sense?
Yeah, well, I'm just thinking if you had, say you had 3 groups in a control, you would have to do this separately. Wouldn't you?
Well, you'd do it the same way. You'd have 3 independent variables then, right?
Okay. But if you didn't have a control and you wanted to reference each one,
so then you have to ask the question, which one of these are the reference group? Do you want to make one of these the reference group? And if you do, then regression would be a perfectly fine way to analyze the data. If you don't, if you want to make all possible pairwise comparisons, then ANOVA with some post hoc test would probably be a better way to sort of more easily get at that. You'd have to run a couple different analyses here to get all of the possible comparisons. Does that make sense?
Mm-hmm.
Michael, did you have your hand up?
Well, I show with the R square being so small, but it still being significant, does that indicate that your n size was probably really big? Or not necessarily?
The n isn't all that big. It's what, 180, 190 or something? Degrees of freedom are equal to what? 180, so it's 190. It's 189 plus 1. So the n was, so it's 0.03, which that is small, but it's greater than we'd expect to get by chance. If we were just sort of flipping coins, or if the internet sites had no influence on the participants, then we would expect R squared to not be significantly different than 0. So is this something that you'd brag about in terms of effect size? No, but it's not. It's something that would get reported, and in fact did get reported in the literature all the time. You'll find a lot of effect sizes that could be smaller than that. If I did have n equals 1,000 and the effect size was half that big, it probably would still be significant. Just given I'd have additional power.
So you wouldn't like write your whole paper based on that, but it might be something
might.
You might?
I might. I mean, it's great. A lot of whole papers have been written on r square less than 0.034. I can assure you. But it's not. It's the key is based on this, it's significantly different than 0, right? There's a chance that it can be 0, but the chance is pretty slim. We have only about a 3% chance of making that error if the p-value is 0.037 or closer to 4% chance. But you're right. At the end of the day, this isn't something that you would be particularly surprised to find or excited about. And by surprised, I mean people's attitudes about politics don't change by viewing a website for a few minutes. And so you wouldn't expect, you see George Bush's website and all of a sudden your ideals about the world and politics change and you have this, the sea change. You just wouldn't expect that given the nature of human beings and politics. And Kristen, did you have?
Yeah, but I think it's dumb. I mean, it's a dumb question. So if you did what Elena said and had more groups that were dummy-coded, no matter what, that constant is what it would be if all of your IVs were 0.
That's correct.
Okay.
That's correct. What part was dumb?
That part. All of it.
Meaning?
It was a dumb question. I should have understood that intuitively.
Yes. No. You shouldn't have. That's my job to explain that, and I wasn't quite sure who or what you were calling dumb, and I just wanted to make sure
Just myself, so I'm glad you agree.
I didn't actually. We're good?
I'm good.
All right. Other questions that I can sort of stumble on and embarrass myself about or not answer or go on and on and on about? So far, so good then with this? Yes? So we see that the constant is equal to the mean of the reference group, right? The constant 5.715 is equal to the mean of the reference group. And that makes perfect sense because when Bush and Gore are set to 0, that's the group that's being referenced. And that's also, I think that's also useful to think about in terms of then the best predictor of the control condition would be the mean of the control condition, right? It's sort of that thing that we talked about. We spent maybe too much time on last week talking about absent any other information, the best predictor would be the mean of some group or of some thing that we're interested in examining, and that's what we find here. So with only demi-coded variables as IVs, the constant of the y-intercept is the mean of the reference group. With only demi-coded variables as IVs, and that's an important qualification. With only demi-coded variables as IVs, the V associated with a given demi-coded variable represents the mean difference between the given IV and the reference group. So we can see that the difference between the Bush group or the Bush condition and the control condition is not significantly greater than 0, right? And we can see that because that B of 0.079 is not significantly greater than 0, right? And that 0.079 would be the difference of Bush minus control, right? Gives us 0.079. Does that make sense? Bush is 5.79. Control is 5.72. Bush. So those two, the mean difference there is going to be equal to the mean difference that we have for that particular variable. Make sense? Cameron, were you thinking about raising your hand or?
Why wouldn't you just do a t-test to get that difference?
Well, we'd have to do two t-tests, right?
So
You
one
could,
test is
you
better than
could, you
two.
could. It would be a preference that the researcher, or you could do ANOVA, right? And you could do ANOVA with planned comparisons, right? So it would be the researcher's preference, right? What is your, how do you want to do it? You could do two t-tests, you could do ANOVA with some postdoc, or you could do this. And at the end of the day, you'd come to the exact same conclusion in all three cases. So there isn't a particular benefit of one over the other, I don't think. The one benefit for ANOVA over regression is the example that Elena brought up, where if you have, if you want to make all possible comparisons,
Right.
you can do that easy with pairing. Or it's actually, because we're not going to talk about interactions in the regression context. We'll talk about interactions in the ANOVA context. You can do interactions in the regression context, but in ANOVA context, they're done for you automatically, right? So you have two independent variables, and if you don't tell SPSS anyway any different, it's going to calculate the interaction between those two. So there are some, and we'll talk about this when we start talking about ANOVA. There's some clear cases, I think, where ANOVA makes sense. I think there's some clear cases where regression makes sense, and then there's a bunch of stuff in the middle where whatever floats your boat, whatever makes the most sense to you. Maybe, for me, if it's a political science or a political science kind of, regression is just what they do. If you're publishing in something that's more geared to psychology, they're much more likely to use ANOVA than they are to use regression. So some of those considerations probably be helpful as well. The good news is, regardless, you come to the same substantive conclusion. And then the only other thing that we have left to examine is the Gore condition, right? And we can see that that difference is significant. So the people who viewed Gore's website, had a less favorable. Is that right? The people. So this is the control. This is Gore. The people who viewed Gore's website had a less favorable impression of George W. Bush than the control condition, because 5.02 is lower, meaning less favorable. And that difference is greater than we'd expect to get, and that difference is the same as this number here, with some rounding there. Okay. Questions? Questions? Probably more typical than just doing an experiment would be data that is not experimental or survey data. One other thing that, and then I'll flip back, one other thing that a researcher might do here, but it changes the interpretation of the constant, is analysis of covariance. And we'll talk about that when we talk about ANOVA and COVA. You could add other control variables here, and you would end up with the same results as if you were to do an ANCOVA using the ANOVA framework. Okay, so you can add you could add other independent variables here, and they would be likely things that you'd want to control for. Maybe there's something that in your experiment that you couldn't control for, and you want to try to statistically control for that, you could do that. And again, the results would be the same. The interpretation would be slightly different, but the results would be exactly the same as if you used ANCOVA out of the ANOVA framework. Jackie, huh?
No, something.
Are you sure?
Yeah.
All right. So here is survey data, and let's just look at. We won't go through all of these, but the bolded variables are dummy coded variables, and so the way that the interpretation of the B in this case is the mean difference between the IVs and the reference group after controlling for the other IVs in the equation. So what's the reference group for female? Male. And so that's the mean difference between males. That's the mean difference between females and males after controlling for all of the other independent variables in the analysis. And is that mean difference greater than we'd expect to get by chance? No, there's no significant difference. So the dependent variable here is how many call people on the phone, ask them if they'll list the most important issues, political issues, public affairs issues that concern them today, and just count those number of issues. So one person might have 5, and somebody else might have 2, somebody else might have 6, and we call that issue salience. How many issues are salient in a particular person's calculus regarding politics. And so in this case, we'd interpret this coefficient as indicating there's not a significant difference between females and males after controlling for education, age, interest in politics, general political knowledge, all of the other independent variables. There's not a significant difference between females and males, right? Does that make sense? The next set of variables, Democrat, Republican, and Independent, is the implied group here, or the reference group. And are there differences between Democrats and Republicans and Independents? What are the differences? What are the differences?
Democrat is significantly different.
Yeah, and more or less, greater or fewer issues that are salient?
Small.
Yeah, because the B is positive, right? And so that indicates that Democrats compared to the reference group, in this case independents, Democrats, when compared to independents, while controlling for, you got to always say that, because if you just did crosstabs and looked at the raw data, the difference wouldn't be the same because it's not controlling for all of the other variables. So Democrats, when compared to independents after controlling for all of the other variables, Democrats have a greater number of issues that are top of mind for them. Jackie?
Did you say, where did we get that we were comparing them to independent?
Because I just said that because that's the reference group or the
So
implied.
you can't get that from looking at it?
No, because you could probably get it from female because it has to be male, but Democrat, Republican, you may not know that the implied group is, it could be the Green Party or whatever, but it is independents.
So from this, we can't compare Democrats and Republicans?
Unless you wanted to make Democrat or Republican the reference group and then have independents be the not reference group, and then you could make that. But can we make all three? Can we do Democrats, the Republican?
That's when you have to use a NOVA,
Yeah. you do
Right.
something else.
if you wanted to compare all three at the same time.
You'd have to use, in this case, analysis of covariance, so you can covariate for everything else. But yes, that would be the way that you could have one independent variable. That would be political party identification, and then you could make that comparison and compare Democrats with Republicans, Democrats with independents, and Republicans with independents. Make all three comparisons.
Was IN political info?
The internet, political, using the internet for political information, it's just dichotomous. Either they do or they don't. So does that sort of intuitively, does it make some sense? Jackie?
What did you say though with the slide before when you're talking about the constant b, the negative 0.261, that's equal to, I thought that was equal to the
Yeah.
independent, or the one that we were comparing it to, but if you don't know what.
Yeah, and so the key is when you only have dummy-coded variables, with only dummy-coded variables, the constant is the mean of the reference group. We have a lot more than just dummy-coded variables.
Oh, okay,
So
it's only if you were just looking at the Democrat and Republican constant. So if on that chart it only had Democrat and Republican, the constant would be the independent.
That's correct. It would be the mean of issue salience for independence. Very good, exactly. Brianna?
So for the female category, did you coded females as 1 and males as 0 because it's still a category of gender or sex, right?
Yeah, it's female is just coded high, and you could do 2-1, but it's in this case I always do call it female
Yeah.
or male, but whatever you call it, make that high,
Okay.
and it would be 1 or 0 or 2 or 1. You can do whatever you want. The results I always do 1 and 0.
Okay. So you could have just called it sex and know that females are 2s and males are 1s.
Then you have to explain to the reader
Yeah.
what is coded high, right?
Yeah.
So they can interpret it.
But
And so
there's no difference. There's no change. It's the same kind of process.
exactly. And for me, it just saves a step when people see that it's female, they know female is coded high, or I could do male, and they would know male is coded high, and so they would know what the difference is in reference to. And it's probably more of a, well, I see it pretty consistently in the literature. I see a lot of people call it gender, or a lot of people call it sex, and then don't tell you what the what's coded high, and so you really are sort of left not knowing. In most cases, it's just a control variable that we just want to control for anyway. So it's not. There's probably not hypotheses that are being tested,
Yeah.
and if there were, then for sure they would explain it.
Yeah. Okay. I'm asking just because I have just a dichotomous IV in my data set.
And what's the IV?
Best friend versus acquaintance. Friendship type.
Yeah, and so you might call it friendship type, and then just
I did,
what's that?
which I did.
Yeah, because for me the reference group isn't intuitive, right?
Mm-hmm.
Female, the reference group is intuitive, I think, for most of us.
But that won't matter if you do 0s and 1s or 1s and 2s.
What would matter if whatever's high, as long as you keep if 1 is female and 2 is female, then the results will be exactly the same.
Okay.
So let's say you did 1s and 0s, and 1 was female, or if you did 1s and 2s were females,
Right.
this result would not change 1 iota.
So if you have a dichotomous variable, regardless of what it is, in 1s and 2s, there's no need to recode into 0s and 1s.
Zero need.
Okay.
The results will be exactly the same. You just have to remember what was coded high to interpret it. For whatever reason, I always just do just 1s and 0s and call it whatever the high variable is, as long as it's intuitive. So we're good? Other questions? So let's look at, it should be the last page of week 6, the assignment. Due on the 18th. Why do I have the 14th stuck in my brain? So I looked at it and I said, oh, it's wrong. It's 14th, but I just have, it's the 18th. I don't know what my problem is. So I'm due on the 18th, a week from this Friday. So use the same analysis that you used for assignment number 2. Unless you're utterly dissatisfied with that and you want to use something else, I probably won't notice. I haven't them all memorized, but I would suggest using the same analysis you did for week 2. And assess the collinearity or multi-collinearity using the 2 different approaches we're going to talk about here in a minute. Determine if you have residuals that are outliers, something we'll talk about in a minute. Assess if there's a disproportionate impact of some of the individual cases. Be certain to fix, to the extent possible, any of the issues. So let's say you do identify some issues with, I don't think I saw any problems with multicollinearity. Most of you asked for those diagnostics in your output, and I didn't see any problems. But maybe you find a case that is problematic in terms of extreme residual or it's a disproportionate impact. You should fix that, and then you'll have to rerun the analysis. Interpret all relevant output and write the results as if they were part of a manuscript being sent to a conference or a journal. And then include your well-organized and annotated SPSS output, okay? Questions? Easy enough?
We'll see. I don't know what any of that means yet.
You have some intuition though, right? My favorite word. You have some intuition of what it means. You'll be just fine.
Yeah, I have a question. So, in determining your outliers for a residual, so you would look at the individual case for an outlier, and then you would do a residual analysis specifically of that case. Are we going to talk about that now?
We're going to talk about it now.
Okay.
Yeah, we're going to talk
Sorry.
about an approach to use. But that's
Because I thought
essentially.
we already talked about it.
We did calculate residuals, right? And you rightfully commented that we should want residuals to be, in absolute terms, small, right? Small absolute value means high R square, all things being equal. And yes, we're going to talk all about how that process works.
Go for it.
So the key here is that we want to ensure that we're meeting the assumptions of regression, that we have confidence, that others can have confidence in our results, that they're not, idiosyncratic to one data set or based on, one case, one person moving my 0.03, p equals 0.0, or what was my p equal? 0.0, what was it? 0.039. Maybe I had just one person that moved that from 0.06 to 0.039 because they were an extreme score. That would be, people wouldn't have confidence in your results if that were the case, right? That one person made the difference between this being significant or not significant. So that's the thing we want to avoid. And I think there's 2 ways to do that. First, by examining your data, and a number of you re-examined your data again for the regression analysis that you did this week, and so I think that's good practice, and that's the proper way to build the regression equation, is to first assess your data for systematic missing data, univariate or multivariate outliers, and normality using those tools that we talked about several weeks ago. And then run your analysis, and then examine your data, and take appropriate action for problems related to, and by examine the data, it's going to be what we're going to talk about here in the next few minutes, or the next little while. Examine the data and take appropriate action for problems related to the collinearity diagnostic that you do, the outlier analysis you do, different outliers than we talked about here, potentially, that's extreme residuals, and then cases that have more influence on the data than other cases, okay, or disproportionate impact. And you'll find that in a lot of cases, but not every case, outliers are also influential cases, but not always. So it's useful to examine both for outliers and influential cases. And if you have cases that are univariate outliers or that are determined to be multivariate outliers here, if you leave them in the data set, in all likelihood they're going to come up again when you do the residual outlier analysis or the influential case analysis. So in some cases, fixing it here will save you from having to deal with it again here. But if you decide not to fix it here, you're probably going to address it again or run up against it again when you do this analysis. All right?
So does it mean like if we have already group, I mean, we are kind of allowed to use the one we already kind of created. We don't have to show the procedure over here.
So you're talking about the assignment? Yeah, and so I'm assuming for the assignment, you've already done this, right? And most of you have. You used either the exact same analysis you used several weeks ago when we did this, or some people use different analysis and we did this. We did this analysis, and some people I think did new analysis and they didn't redo this, but I would suggest, and I didn't require that you did. In fact, I said I would have no way of knowing whether you did or didn't, and so you don't have to redo this if you've already done that, right? Is that?
Even if I have, well,
Like you don't have to write about it.
In the real world, you'd redo it again, right? Because if you haven't done this, you need to redo it again, right? But in this class, I'm not going to require that you redo it. It ends up just taking more time than I want you to take to do. But in the real world, if you're trying to publish this, and you change your variables, you need to do this again, right? In this class, so we're just talking in this class. I don't require that you redo this again. Many people did if they had new independent variables and dependent variables. So I don't think I answered your question.
well, like I was just wondering about the I'll ask again, maybe.
Okay.
I was just waiting.
Yeah, on break or something, ask me, and so clear enough in terms of what I expect for assignment number 3 in terms of analysis, because I think that's what the question related to, right? Clear enough?
So if we did change variables, but we didn't necessarily want all of those, you want us to do both?
Don't
You
include
should-
that in your report, right? Just include the.
I'm going to assume you already did this for homework assignment number 3. It's on you whether you do it or not, okay? And in the real world, you would always do it again, right? But for a class where you have competing interest with other classes, I'm not going to make you or require that you do everything 3 times because you didn't pick the exact right set of variables for one of the earlier assignments, okay? Jackie, does that help?
Yeah.
All right. the yeah was
Yeah.
not particularly expressed with confidence, but you don't have to do it again, right? I don't expect you to give it to me, okay?
But I mean, you're essentially looking for the same thing in both of them anyway.
You'll see that the procedures are much different. What we're going to talk about for collinearity diagnostics is much different, and that is a different thing than we talked about in terms of it is
But
not
it's solving the same problems with the data.
similar issues with the data. Yes, collinearity is a little bit different, but outliers and extreme case residual analysis is very similar to looking at outliers in sort of that work that you do before you ever run your regression. Okay? So if you have questions about whether you need to do something or not, send me an email, call me, ask me after class, and I'll clarify if there's confusion about what you should or shouldn't do for this homework. But you don't need to write anything about doing this in homework number 3. Okay? You don't need to tell me anything about it.
I got it.
I'm going to assume you've done it, right? So multicollinearity, or I think some people call it collinearity for short. Some people I've seen, this is the way I was taught. It's multicollinearity, collinearity for short. Some people refer to collinearity as just being 2 variables, multicollinearity as being greater than 2 variables. In my experience, people use the terms interchangeably. So call it multicollinearity, call it collinearity, but it has to do with the adverse effects of highly correlated independent variables. Only concerns the independent variables in your analysis. Does not have anything to do with the dependent variable, only concerns independent variable. There's no hard number that I can give you in terms of a correlation that is too high, other than, well, we'll look at some hard numbers, but their numbers are really, really close to R is equal to 0.9997 would be too high for it to be run. It would also probably cause problems. So really the best way to determine whether you have issues is to not look just at the correlation coefficient, although that's a good place to start, and but to also look at the diagnostics that we're going to look at here in a minute. I do indicate greater than absolute 0.7, so it doesn't matter if it's inverse or a positive relationship. But just because it's 0.7 or greater doesn't necessarily mean that it's going to be a big problem for you, right? It just, 0.7 should be a place where you start really paying attention to what it is that you're examining in your analysis and making adjustments if need be. And then run the diagnostics to see if, in fact, it's causing problems or not, okay? Singularity is the idea of perfect correlation between some group of variables and some other variable. So if we dummy coded up, if we didn't leave out the k minus 1 group, and we did, let's say k is equal to 3, and we coded up 3 variables, that would lead to this thing of singularity, because 2 of them would be perfectly correlated with one of the other ones that were left out. Highly correlated independent variables cause both concerns or issues logically and statistically. From a logical perspective, it just seems, by and large, there are surely exceptions to this, but why would you want to include 2 nearly redundant variables in your analysis? And if they're highly correlated, even if you're calling them different names, if they're highly correlated, they are nearly redundant measures of one another. And so, it doesn't, logically, it doesn't make sense to include two measures of the same thing in an analysis. Even if you're calling the things two different things. You might be insert any two names that you want for variables, but just because you call them different things doesn't mean that in terms of measurement, people perceive them or that they're being measured as different things. So it does at least call into question why one would want to have 4 independent variables that are all, correlated greater than 0.7, all move up and down with a great deal of consistency. One has to at least ask the question, does this make sense logically from a research perspective? Are there some measurement issues going on with validity? Maybe you think you're measuring something that you're not. And again, just because we call it a different name doesn't necessarily mean from a measurement perspective that it is different. And if it's highly correlated, I would suggest that the differences are probably minimal. Jerry?
Oh, I have one question on that. It seems to me like if you had a couple of different variables and they were very tightly aligned, correlated, it would also be an indication that you have something very strong going on here because it's happened here and it's happened here. Proved it twice.
Right. And so is that an argument for including them in the analysis together or not? I mean, if they're both getting at the same thing, whatever that thing is, my argument, and I say by and large, not this, there's gray area here. Some theory might suggest, or maybe the past research has always done it this way, and you're just going to follow what past research has done and include several indicators of things, even though those indicators suggest that they're highly correlated.
When you say redundant variables, though, do you mean like the same thing measured in the same way? So, like what I'm thinking of is in Jerry's example, GPA and IQ. Like we're trying to get at some intelligence level here.
Yeah.
They're measurements.
Yeah, and so there would be I don't know what the correlation is between GPA and IQ, but it's not greater than 0.7. Somebody could Google that, probably find that out for us. But it's probably, but those to me are very different things, right?
Right. So that's not what you mean by redundant variables.
If they were, let's say we had data and the GPA measure and an IQ measure were correlated at 0.75, then I would have to start wondering. Well, I'd have to ask some questions about what's going on. But those are two quite different things, and I'd be surprised in a real-world context if GPA and IQ were correlated. They're correlated, sure, but I don't know that they're correlated quite that strong. But that would be, and then the researcher, it's all on you, right? The researcher has to make the judgment. Okay, these are correlated. The correlation is quite high, but I'm going to keep them in and then make an argument as to why you need to keep them in or not, okay? Did anybody Google the correlation between GPA and IQ? Nobody's done it?
0.32.
What is it?
But that's, I don't know if that's 0.32.
Yeah, I don't know what it is either, or what I don't know what, there's not an is. It would vary depending on the school you were at and a whole bunch of things. But I think that's where common sense would come into place and have to think about, okay, this is GPA, this is IQ, these are two theoretically quite different things. Even though the correlation is maybe high in a particular case, you'll have to make the judgment about whether to keep them in. And then the other thing that would be a part of that is how much of an influence are they having on your results? And so logically, one needs to consider what's going on, and then statistically, one needs to consider what's going on. And from a statistical perspective, highly correlated independent variables inflate the standard error B, And what problem will that cause? So highly correlated independent variables inflate standard errors, which would cause what problem? What do we use standard errors for? We use standard errors for
T-value.
t-values, right? Because it's a ratio of t over standard error.
Go down.
It's the ratio of b over the standard error of b. Yeah, and so probability values would end up going up. T-values would go down, right? So that would be the consequence of, or one consequence of having highly correlated independent variables. Another consequence is beta weights or beta values can fall outside the range of -1 to 1. So we think about beta as being like a correlation coefficient, and correlation coefficient, Pearson's R, is constrained between -1 and 1. Mathematically, it can't be less than -1. It can't be greater than 1. Same isn't true for beta, and so you can end up with beta values that are far outside of the range of -1 to 1. And that would certainly draw a lot of red flags if you're going to report your beta values in your research report and you report a beta value of 100. People would take note of that, and people that are informed would probably ask questions about why is this the case. So statistically, it causes probably the problem that's most frequently discussed is inflated standard errors. But another thing that's also would be true is beta values that become outside of that range of -1 to 1. There's no agreed on criteria for the level of correlation that's too high. That 0.7 is sort of a rule of thumb that you can keep in the back of your mind. However, perfectly correlated independent variables will not generate a solution. SPSS will kick it out. It's actually like trying to divide by 0. It's not a number, and so it causes, it can't do the math, and so it says I need to fix this, and so it throws out one of the variables to fix the problem of the correlation between some set of variables and another variable being at absolute 1. Brianna?
Is that the same? It'll throw it out and be like dividing by 0 if it's perfectly negatively correlated?
Yes.
Okay.
Yeah, and so it's absolute 1, and it's a phenomenon similar to trying to divide by 0. It's not actually trying to do that. It's trying to invert a matrix, and it can't do that when two variables are perfectly correlated. And the analogy that I use is like trying to divide by 1, or taking the square root of a negative number would be another sort of intuitive way to think about it.
How often are two variables perfectly correlated?
If you dummy code a variable and you include all 3 of them, let's say k equals 3, and you include all 3 of them, this would indeed happen. In the real world, the only time it happens, I think, is sort of researcher error, right? Researcher does something with the analysis, puts in 2 copies of the same variable or some dummy-coded variable that is redundant, and I don't think measurement tends to be, almost never is perfectly correlated. Other extreme correlations are also too high, so this is the limit that you can change it, and we'll talk about what you can change in SPSS. But if you try to run an analysis with 2 variables that are correlated that high, SPSS will say, hey, there's a problem here, and it will not throw an error message. It will just send a warning saying that it excluded some variable, and then it would run the analysis for you with that variable excluded. Okay?
I have a question.
Yes.
So what if your independent variables have higher correlations than your independent with your dependent variable?
The correlation between the independent variables is greater than the correlation between the independent variables and the dependent variable. As long as the correlation between the independent variables is not causing multi. I'm sorry.
None of them are greater than 0.7.
Then you wouldn't have any issues in terms of. Well, you'll have to look at the collinearity diagnostics that we'll look at to be sure. But assuming that they're okay, then there is no problem interpreting your analysis as being a valid analysis, even though independent variables are more strongly correlated than the independents to the dependent.
So that doesn't suggest that maybe you should redo your model?
Not automatically. I mean, we could come up with some cases probably where it would, but to me it doesn't mean that automatically we should. And a lot of times, if you the multiple regression we looked at, where the dependent variable was that issue salience, the correlation between a lot of those independent variables in that analysis, the correlation is very high.
Yeah.
Correlation between general political knowledge and education is high, and higher than the correlation between general political knowledge and so.
Okay, that makes sense.
Good question. Other questions? So first we'll examine this thing that we call tolerance, and that is an indicator of multicollinearity. And then 1 divided by tolerance, or variance inflation factor, we'll also talk about as well. And so there's really 2 different statistics that SPSS reports. If you remember those 2 columns on the far right, it reports tolerance and VIF, variance inflation factor. Well, variance inflation factor is just 1 divided by tolerance, okay? So we'll talk about tolerance, and then you'll know where variance inflation factor comes from, because it's inverse. So tolerance, and this is the sort of the intuition of how tolerance assesses the correlation amongst your independent variables. Tolerance for a given independent variable is computed with multiple regression by making that independent variable, that given independent variable, the DV, and keeping the other remaining independent variables as independent variables. And then the R square from this equation, is subtracted from 1 to get a tolerance value. And so it's finding out what's the R square between some set of independent variables and another one of the independent variables. And then it does 1 minus R square to get the tolerance. Okay? Make some sense? Let's try to do it. We'll do it for one of our variables. And I think if we sort of walk through the logic, you can sort of see what I mean. So this is the same analysis that we worked with last week. Dependent variable is how often somebody attends religious services. The tolerance value for how often they pray is 0.8. So what should the R square be? 0.2, yeah. So we're gonna do the analysis where we get rid of this dependent variable, make this the dependent variable, keep all of these as independent variables, find out what the R square is, and the R square will be 0.2. We're close to it because that's and does that make sense, how that's assessing the correlation between these independent variables here and the one that we're assessing? Because it's just, that's what R square is. It's the correlation coefficient, really multiple correlation coefficient amongst some set of independent variables and the dependent variable. And so it's just a metric that allows us to find out if we have issues with highly correlated independent variables. And so this is the data set. I have to make one because the case-wise, if we take the dependent variable out of the analysis, my list-wise n is going to be different than the list-wise n that I would get for this analysis, and so I have to make sure that the analysis is being done. If I want it to match what we were doing earlier, or what we looked at just a minute ago, I have to make sure I'm working with the same set of data, and we're no longer going to be looking at that dependent variable, religious service attendance, and that variable had some missing data on it people were being excluded because of their missing data on it. So I just had to make sure that we have the correct sample so we can get something that's fairly close. And so the dependent variable I said would be how often they pray. And then the independent variable will be 2, 4, 5. Is there 5 remaining? So 6 independent variables total. Is that right? And so that's the R square, which squares or matches the variance. And so variance or tolerance is 1 minus R square. And that's where the 0.8 comes from. And we could do that by hand for all of them if we wanted to. But why would you when SPSS does it for you? And then 1 divided by 0.8 should be 1.251. And so that's what variance inflation factor is, okay? So the inverse of 0.8 is 1.251. Don't ask me why. Why couldn't we just live with tolerance? Why do we also have to have variance inflation factor if it's just the inverse? But there probably is some long and not very interesting story about struggles in mathematics and that sort of leads to that. But in the literature, I see variance inflation factor reported more often than tolerance. But you see tolerance sometimes too. So the smaller the tolerance, the greater the level of collinearity, right? Because we're doing 1 minus R squared. By default, SPSS excludes independent variables with tolerance levels less than 0.0001.
If that happens, will it tell you?
Sends a warning message. It still runs the analysis, and then it's not a very some warning messages sort of shock you because it's just some bolded print underneath one of the tables. Probably, well, I think it's in a couple places, but the table with the B's in it for sure, and there'll be another table that shows excluded variables. And so it's there, but it's not as prominent as, sometimes I've missed it until I start looking through my data, and where's one of my independent variables? It went missing, and then I figured that it went missing because the correlation was too high. It can be adjusted if you want to. So let's say you have good reason and you want to run the analysis, you can adjust it with syntax to a much smaller number. Extra credit to anybody who knows what would it be? 6 zeros, 0.000001. So you can adjust it to that low if you want to. And if you Google changing tolerance values in SPSS syntax, you can find out how to do it. It's just a little snippet of code. You could run the analysis with the graphic user interface, save the syntax, insert that one little bit of code about adjusting the tolerance value, and then you could rerun your analysis, and then you wouldn't have assuming it's the tolerance is not less than 10 to the minus 8. Okay. Sometimes, for example, when we talk about nonlinear regression, oftentimes there's issues with tolerance with nonlinear regression because we're using a variable and then we're just squaring that same variable and using it as an independent variable. And so that can cause problems with tolerance. So can interactions cause problems with tolerance. And so sometimes it's not just because of error on the part of the researcher. Sometimes you're actually trying to do something and you know what you're doing. That would necessitate you having to change that value. Tolerance values less than 0.1 should be a cause for concern, or at least take a look at. And the inverse of 0.1 would be 10, right? And so variance inflation factors greater than 10 should be a cause for concern. Or even if it sort of gets to, I mean, I would look at it if these were even, there's nothing there that would in any way be concerning because nothing's even close to 0.1. Nothing here is even close to 10. But let's say something was at 9 or 7. I would sort of want to at least take a look at it and then make a judgment. But less than 0.1, there's no rule. You'll have to judge, maybe the judge on what to do. Brianna?
So if we use 0.1 as our guide, as our criteria or whatever, that means the R square is 0.9.
The R square between that independent variable and the set of other independent variables is 0.9. It's quite high. And so, but that's the sort of standard criteria that are given out. So that's, but if it's 8, is that 7, 5? Where would you be comfortable?
Yeah.
3?
I was going to say, I read 3 before. When I was writing my thesis, they told me that 3 would be
0.3?
or 3 variance inflation factor.
Yeah.
Which is 0.32.
Right. And so you'll have to just become the judge of what you're going to do in what situation. I wouldn't automatically say less than 0.1 automatically means you exclude that variable from the analysis. That is going to be based on your theory, your research, whatever it is that you're trying to do.
That just seems crazy. I mean, it makes sense to me that if you've got a tolerance value less than 0.1 and 90, I mean, that says the variance between that new IV, which is treated as a DV, or whatever, that way, like 90% of the variances explained between them is huge red flags to me.
It is.
And even a 0.8.
And a 0.3. A 0.3.
I mean, that 0.1 just seems super crazy to me.
It's too low.
Yeah.
So make it higher.
You do what you want.
But it's still, at the end of the day, each scenario, each context will require your expert judgment in terms of what to do. And I wouldn't say less than 0.1, automatically exclude them. That just would not be, because there'd be plenty of contexts where you wouldn't do that. But I agree that if R squared is 0.9,
I just think to get a 0.9 in socio-behavioral research, in communication research, I mean, we can't get that.
yeah.
We have the best theory ever, we can't find, I mean, that's huge.
Right. And so it probably the only way, well, it can happen in a number of ways. These are more typical of what you see in Cameron, did you have any 0.3s in your?
Very close because I had satisfaction and commitment both were, and they're highly correlated.
Yeah.
Which is why we went with the conservative number so I could make a stronger argument for keeping both in the model.
Yeah, and it did approach.
It was getting close.
Yeah.
But no.
Michael, you said that yesterday or last week that you had a couple independent variables that you thought were highly correlated. They ended up not being highly correlated. Or they're maybe still highly correlated, but they didn't cause any problems. Actually, the correlation wasn't that high, was it?
It was like, probably close to 0.39.
So the correlation between the independent those two independent variables was 0.39.
Yeah, about there.
Do you have your output in front of you
No,
from
I
the
do not.
homework? I was just curious as to what the tolerance level was for those, but it probably wasn't much. Probably wasn't much. Pretty close to these. It was smaller than 0.8, I assume, but maybe certainly not 0.3, and nowhere as close to 0.1. Okay. Other questions? We're good? So another way, so that's homework assignment number 3. I say use 2 criteria to assess multicollinearity. Criteria number 1 is tolerance, and 2 isn't its inverse, variance inflation factor, okay? 2 is the next one that we're going to talk about, okay?
Okay.
So 2 would be another, when you ask for collinearity diagnostics in SPSS, you get the variance inflation factor and tolerance that are tied to the end of the table with the B's and the betas. And then you also get this table, or the table that looks like this table. And I've actually done a little bit of research to see if there's an intuitive way to explain how how these numbers are derived. There's a void of information on how the table is derived, and what information I have found about it is not very intuitive. So the approach that I'm going to take is the same approach that somebody took with me a long time ago. They just said, here's the criteria you use, and just apply that criteria to this table, and you'll be able to assess whether. And so you have to sort of trust that this table knows what it's talking about. I think that's probably a fair trust to make. And so the second approach, without explaining the origins of the data in the table, is to assess collinearity diagnostics by examining the condition index, this column. We don't use the eigenvalues at all, and they're pronounced eigenvalues, not eigenvalues. But eigenvalues are a measure of explained variance. We don't use the eigenvalue column at all. We use the condition index column, and condition index is greater than 30 for a given dimension, coupled with variance proportions greater than 0.5 on these two different variables, and we don't include the constant, okay? So these are, the condition index is sorted from smallest to largest, and at the bottom of the table we can see that our largest condition index is 0.2. We have no problems with collinearity with this analysis, because none of these are greater than 0.3, okay? Or none of these are greater than 30. None of these are greater than 30. So that's the first thing we're going to check. Look for condition indexes that are greater than 30. Look at the largest one, and then compare across the variance proportions to find variance proportions that are greater than 0.5.
So what happens if, so one of mine is like 24, and then it's 0.4. They're all, but if it's not greater than 30.
So 24 is, for me, is sort of close to 30.
it has to
So
be both of those.
so the first thing you would do is the largest one is 24.
Yeah.
And then I would go across the table, and are all of these greater than 0.5?
0.72, 0.94, 0.03.
So 2 of them are greater than 0.5. Those 2 that are greater than, there's 2 that are high, 1 that's low. The 2 that are high means there's a high correlation or a higher correlation amongst those 2 independent variables. And so you would have to be the judge of whether that's a problem. I think if it were me, I would use both methods. You could look at the tolerance or its inverse, variance inflation factor, and look at these diagnostics. And if they both clearly indicate concern, you probably should address the concern. If they both indicate no concern, then you have nothing to address. But if one looks like it's a concern, one doesn't look like it's a concern, then it's going to be incumbent on you to decide what to do in a given situation. And obviously, that can't, those situations will change. So what I did, so there's no problems with this analysis with collinearity based on this table or on this table. Just to change things up or to cause some problems, I took the age variable and I squared it. And I took education and squared it. And we can now see that some of our tolerance, what's the number we should be looking for here? 0.1. We have some tolerance values less than 0.1. Not surprising. Those tolerance levels are associated with age of the respondent. And if we square age, the square of age and age aren't correlated at 1.0, but they're both highly correlated, just like levels of education and its square are also correlated. So clearly suggests some issues here. And then if I look at this table, I would always start with the highest number, which would be the number closest to the bottom of the table, the condition index of 70, scroll across to find values greater than 0.5. And we find this is 0.91, and then what is education?
0.88.
Yeah, so education and square of education, 0.88, are clearly a problem, and we can also see that if we look at another one that's greater than 30, 55 for dimension 8, we have 0.9 for age, and we have 0.9 for age squared. So not surprising, including the square of age of education causes problems with collinearity. And that one would be easy to fix. Questions about collinearity, multicollinearity, Michael?
Oh, then like with all these calculations, will we have to run a test for each IV, or are we still going to find everything if we just would do the test, making one IV the DV?
Yeah, and so what you'll have to do is you can just rely on SPSS to do the test for you, right? We just did the one test here for our own edification. I'm not asking you, is that what you're asking? I'm not asking you to calculate the tolerance level by hand for each of your independent variables.
Oh no, I'm not talking about by hand. I just mean with running the tests.
You get this in the regression you ran last week, right?
Yeah,
Yeah.
just have to check
We
a
already-
box. You just have to check a box when you do the regression. So it'll show the statistics with it.
Yeah, and so I calculated this one, not by hand, but sort of by hand compared to this because I had to put the independent variable in. And you don't have to do any of that. All you have to do is get SPSS to print these two columns and assess these two columns, okay?
Oh, I wasn't talking about by hand. I just meant like just to check the multi-code linearity, we run a test by making one of the independent variables the DV. Right.
You don't have to do that though,
Oh, okay.
because this is doing that for you, right? I just did it as to demonstrate how the intuition behind where this number comes from.
Okay.
You don't have to do it unless you're so inclined. You can, but it's going to match this, and there'll be no. You'll just waste the better part of an hour doing it for no good reason. Okay. So let's take a break, Jackie, and then we'll take a break.
No, I was just gonna, you can take a break.
Cameron needs
I was gonna ask, can you explain again the condition index?
Sure. So. So we're going to look at two things. Numbers greater than 30 here.
And that's really all we need to know about it.
What's
Just-
that?
That's what you were saying, that's, we're not gonna explain really what that, just as long as we know that,
Yes.
okay,
Do
that's all I
you have any greater than 30?
need. No, the 24 is
Okay. And then, so if we just look at the 24, which we know is probably not going to be a problem. If you scroll across, are some of them greater than 0.5?
Yeah, that's the 0.73.
No way.
And what are those two variables?
You do that. I set up
Maybe.
And the dependent overall happiness.
got my two.
So does it make sense? Are those two independent variables? What if the tolerance
Well, I
level
was
was?
Zoom a couple of weeks ago.
0.294
Uh,
and 274.
My
Yeah,
classes-
so they're sort of close to what Cameron said.
And every time
The
I go in,
criteria
it's got
that he
pretty good
used.
classes and it gives me new.
So that's just, that just means that those two
So I
are very
emailed,
Yeah,
uh,
if it were me,
Yeah.
the theory
and she emailed me
suggested that
back
they should
Friday
be
and
together. You
uh,
probably, what's the, do you know the correlation?
yeah, I
between
can
the
get into your classes, I see.
In your output, which I think I have here, that I put in my box.
Your password.
Yeah,
Our tech department's never seen this before, we're trying to figure it out. So,
What is it?
he goes,
0.831.
well, either we'll get it figured out, or you can go in and create two new classes and send new passwords to
Yeah, it's gonna be hard.
Or go off again.
And
But,
a risk of chance of
but-
it happening again.
Between the
Well, hopefully
independent
they
variables?
figure out.
Oh,
soon.
between the
Yeah, well,
Yeah.
if they don't get done this
Between
class,
those two,
they'll
you
use
can
it
do it.
everything.
Yeah.
Because
Between stable
that'd be for the first one, then for the second one, hopefully they have it fixed.
overall
Yeah,
happiness.
did you,
What's the
did you see my email last week about?
Yeah, I
Okay,
did.
what's the two independent variables that had the
That's
high,
the issue, like,
and its correlation
Oh,
between
it's really
stable and
good.
strong
It's
is
figured that out.
0.831?
Good.
Yeah,
It must have just been
that's pretty high,
another
so
weird glitch.
you would have to make a judgment
I keep
on
thinking
your
we'll
own
run out of glitches.
as to whether
No,
No, we
you'll
never
have to-
will.
But they're somewhat redundant measures, right, when they're correlated that high.
Yeah,
But I think given the, what did you say the variance assumption, or the tolerance was?
0.294, 0.274.
Yeah, I mean, they're nothing to write home about. I mean, they're reason for, but if I look at everything else, so these are a little bit low. We said 0.1, and Brianna said that's just way too low, and so did Cameron agree with her. You're at 0.27 and 29, and then if you look at that, for you, it suggests that there might be sort of an issue because this is 24, right?
Mhm.
So if you're writing this research up, you want to sure mention that two of the independent variables are correlated at 0.3. You assess the diagnostics, and given insert citation, there's no strong reason for concern. But for this homework, from what I've seen, you don't have to exclude anything. Okay. Michael, did I answer your question?
Oh, yeah, yeah.
Are you sure?
So for our homework, do you want to see the syntax of running the regression